Okay, so we have now come to the third proof of Sylow's theorem. So let us see what the basic strategy of this proof is. It's a little strange, but it's as promised, it's going to give us the second and third part of Sylow's theorem, which we haven't seen in the first two proofs. So the strategy is this. First, we are going to prove that these symmetric groups Sp to the power r have p Sylow subgroups, where p of course is some prime and r is a non-negative integer. So that is the first step. Then the second step is that if G is our original finite group in which we want to prove Sylow's theorem, if that group is a subgroup of some larger group M and Sylow's theorem is true in M, then it is also true in G. This is what we will prove next after proving this. And in the third step, we will prove that in place of this M, one can consider one such symmetric group for a large enough K. For some large K. And the choice of this K, of course, will depend on our original group G. So it's of course it will take some time to go through all these things. Today we will see this. And you see, the author is now going to talk about the group Sp to the power k. So instead of taking r here, we are going to take k following the author. All right. Now in considering these groups, we can consider one case which occurs first, and we just see what happens in that case first. Remember, r is any non-negative integer. That means r can be 0 also. That is, k can be 0 also. So that is our first trivial case. In that case, our group is just S1, which is essentially the group with one element. And the only relevant power of p that divides the order of this group is p to the power 0, because in this case the order is 1. So by the claim of Sylow's theorem, there should be a subgroup of this group of order 1, which of course is the group itself. That means our claim is true in this case. So we can now consider k to be a positive integer. I know there is actually no need to show these things, but for the sake of rigor, why not? Now the next question that faces us is exactly what power of p divides the order of Sp to the power k, which we know is this p to the power k factorial. And the lemma with which we are now going to start answers that. So this is lemma 212.1. Now the little notation that the author has adopted here to say what the, to at least write what that largest power of p is, which is going to divide this. I'm going to make it a part of the lemma. It's not how it's given in the text, but let me just write it here itself. Let nk, n of k, be a non-negative integer such that p to the power n of k divides this factorial but the next higher power does not divide p to the power k factorial. That means this is the largest power of p that divides p to the power k factorial, and nk is the corresponding exponent. But then what does the lemma claim? It claims that then nk is this. And we are now going to prove this lemma. In proving this lemma, the first value of k, that is k equal to 1, now assuming that k is positive, it has the least value 1. That is going to be considered first. So let k be 1. Then the power of then the actual number is p itself, right? And if you write it as the product that it is, then you get this. So the largest power of p dividing p factorial is p. We can see that from the expansion. No other factor from here is going to give us any p. Why? Because p does not divide any of them. You see, there is a thing about this product. The fact that p is a prime makes this happen. That's because what example should I give here? Say, suppose you consider this thing. 6, the number 6, right? 6 is not a prime, 6 is a composite number. 6 divides 6, but 6 neither divides 2 nor 3. So you see, 6 is neither dividing 2 nor dividing 3, but 6 divides their product. This does not happen for a prime number. When you have a prime number and it divides the product of 2 or any number of numbers, any number of integers, it has to divide at least one of them. So that is why no p is going to come from here. However, in place of these integers, you imagine 2 and 3, and in place of p, you imagine 6. Although these are not divisible by 6, being less than 6 and positive, but still their product is giving us 1 6. That will not happen here due to primality of p. Okay, so that is why the largest power of p in this case is p itself. And that in turn means what? It means that n of 1 is 1. So n of 1 is 1. n of 1 is one that we are getting from the current situation and the definition of n. But is it matching with the claim? What happens to this sum when k is 1? When k is 1, the right hand side sum has only one term, which is 1 itself, because when k is 1, this itself becomes 1. So that is the only term. So that means in this case our claim is true. So now we can consider these other cases. Do not misunderstand this as an induction proof. Okay, it is not. This is just one starting case which we have considered separately, and now we are going to consider this. This is not induction proof. So now our number is this, and if we write it similarly as a product, we are going to get this. Now there are many factors, many numbers here that are being multiplied together. Which ones among them are going to give us powers of p, or are going to contribute to powers of p? Clearly, any such number must itself be divisible by p, or in other words should be a multiple of p, because you see, if something is not divisible by p, then due to primality of p, again by that argument, it's not going to give us any p, or two such numbers when joined together in a product also will not give us any p. So that's why among these numbers means these individual numbers, you understand from the context, the ones that will contribute to powers of p are the multiples of p, precisely actually. Now let's see what the multiples of p are among these numbers. Of course, they will be p, 2p, 3p, like this, up to what? How far shall we go? Note that the last factor itself is a multiple of p, so we can go that far. We will of course miss some intermediate numbers. They are not multiples of p, but these are going to be multiples of p. And the last one, just to show that it's a multiple of p, we write it like this. So when we say that this number is, this product or this factorial is divisible by some power of p, in fact we know what that power is. Theoretically, that power is this. Then that division of this number by this power of p is going to happen only to that part of this product which involves these multiples of p. That is, if you rearrange the numbers that you see here and group all the multiples of p together, that is where in that region only the division is going to happen. Whatever is not there in that region, whatever does not lie in that region, namely we put the non-multiples of p on one side and the multiples of p on the other side and rewrite the product. It's in this part that this division is going to happen. So that means we should look at the product of these numbers, these multiples, and that product is simply this. This is the part of the original product that is giving us P, many P's. Now you can see that this is nothing but, how many factors do we see here? 1, 2, 3 like that, up to p to the power k minus 1. That many p's also we are getting. So let's write that first. And then along with that 1, 2, 3 like that up to this, which we can write as a factorial. So this is how the number looks in a more compact form. Okay. Now the fact that this number itself has in it p to the power nk tells us something. P to the power nk is the largest power of p that appears here, and in particular it appears here. And we can see that in this number itself we already see a power of p. But there may be more, and that maybe more part lies here, which means that this full exponent nk has one part of it here, p to the power k minus 1, and the other part is going to come from here as this. Why does this look like this? It's because this is again a factorial of a power of p, but where the exponent is the next, I should not say next, but the previous one, the previous lower one. So that is why it is nk minus 1. It's crucial to understand why this is true. You can see why this is true. Let's just go through it once more briefly. P to the power nk is the highest p that we are going to get here in the current situation. A part of it we can see here already, and the exponent is p to the power k minus 1. Whatever else there may be is going to come from here, and itself should be the largest of whatever else there should be. So that actually should be this. Okay, so the entire p to the power nk has one part lying here and the other part lying here, and we have plus because of rules of exponents. So this is now a nice recurrence relation. Now if we rearrange it a little bit, it looks like this. And you can clearly see that if we now change k itself, then we are going to get other such similar equations. And then there will be another one. We're not going to write those things, but eventually we will reach what? You see, because our k is greater than 1, right? So the least value of k is 2. And when we take k equal to 2, we actually have n1. But that is the last point. Before that, we get n2. That we get when we put k equal to 3. So when k is 3, this is p. And finally, there is one n1 also, which we have already found. n1 is 1. Now we can add these equations together. So you can see that on the left side almost everything gets cancelled except nk. Even this last n1 also does not survive. On the right hand side, of course, we have some things. And there is one more thing which may be a little confusing to you. Okay, we understand the meaning of this equation, right? Because we are working with the number p to the power k. However, what is this equation? For this, you just have to think of the similar situation where the number is not this factorial but rather actually this factorial. That will produce this equation, and then the next lower one will produce this equation. Like that it will go. So adding these numbers, the left side will give us nk, and the right side, instead of starting with this, we change the order and write like this: 1 plus p plus p square and so on. And that's what we wanted to prove. Okay, so the proof is over. And now we know precisely what power of p divides p to the power k factorial, which is the order of our symmetric group sp to the power k. And now we come to our main result. This symmetric group has a p-Sylow subgroup. Why am I writing subgroup with capital S? This proof is going to be by induction. But still there is a construction also inside that induction. I mean, at the induction step there is a construction of the group actually. So for induction we have to consider the smallest value of k, and the smallest value of k is k equal to 1. Do not wrongly think that the smallest value of k is 2, because here somewhere we handled the case k equal to 1, but that is in the previous proof. Okay, we only disposed of the case k equal to 0 in the very beginning, but k equal to 1 is still there. And in this case, what is the group? The group is just sp, and its order is p factorial. And we already know the largest power of p dividing p factorial, either from the previous lemma or just by simple inspection. It is nothing but p. So now we need a subgroup of sp of order p, and that is very easy. You consider the p cycle, this p cycle or any p cycle in sp. The cyclic subgroup generated by this p cycle has order p. So that is such a subgroup. And why is that so? Because we know that any p cycle itself has order p. So that means our claim is true in the case k equal to 1. And now we will assume the induction hypothesis. So the induction hypothesis is just this. Let the claim be true for k minus 1, where k greater than or equal to 2 is some integer, some arbitrary but fixed integer. Because we are we are writing the induction hypothesis in terms of k minus 1, so the least value of k should be 2. Alright, so now we want to prove the claim for s p to the power k. So let's see the symbols that are there in sp to the power k. That means the symbols are the objects on which the permutations of this group act. That is this set. We are going to partition this set into disjoint non-empty subsets, which the author is calling clumps for some reason. I don't know why, but maybe it's just a language, that's all. We partition this set into p clumps as follows. Clump number 1. For the sake of clarity, let me give them numbers also. In the first clump, we are just going to consider, we will of course consider the numbers in their natural order, but we stop here. Okay. The second clump starts from where we stopped in the first clump. So we take the next number and then continue like that. Plus 2. But how far shall we go? The clumps should have the same size. So in the first clump there are p to the power k minus 1 elements. So that many elements should be there in the second one also. And we can see that this is the first element, this is the second element. So the last element should be this. Okay. Now the author in the text does not show the third clump, but let's see that. Let's see the pattern more clearly. Just one more. So next we are going to start from 2 times p to the power k minus 1 plus 1, the next integer. Like that till and it continues. And what about the pth clump? let's see in what pattern these things are appearing. When you see the first clump, it is not that clear, but if you look carefully, the first element of the first clump can be written as 0 times p to the power k minus 1 plus 1 because it's 1. The second element looks like this, where you understand that there is a 1 here. The third element starts like this. The third clump starts like this. So, the coefficient of p to the power k minus 1 in the element where the clump starts is 1 less than the clump number. So, here it should be p minus 1 times this plus 1, p minus 1 times this plus 2, and finally this, which if you see, actually it ultimately becomes p to the power k. So we have exhausted all the elements, and this is a partition clearly because the sets do not have anything in common. They are non-empty and their union is this. But why? What is the purpose of this? It's because using these sets we are now going to define a very special element or permutation in sp to the power k. Sigma. Now sigma is going to be a product of some cycles, and in those cycles we are going to use these clump elements in a special order. Let me write the first cycle of sigma. So the first cycle of sigma is going to have the first elements. The way you see, I know that these are sets, so in a set there is no first element or anything like that. But the way we have written them, there is a first element, a second element in each clump. So we are now going to use the first elements of all the clumps to write sigma. So first we have 1, and then we have this p to the power k minus 1 plus 1. Then in the next clump, in the third clump, this is the first element, 2 times p to the power k minus 1 plus 1. Like that it goes, and finally the first element of the last clump, p minus 1 times p to the power k minus 1 plus 1. But that's not the only thing in sigma. There are other cycles also, times. Now in the next cycle we are going to use the second elements of the clumps. So the second element, of course, in the first one it's 2, in the second one it's this, then in the third one, so that plus 2 is constant, it's going to stay there, just like we have plus 1 here. And finally this one. And if we want, we can write a third cycle, but no need. Like that it goes, and finally in the final cycle we are going to use the last elements of all the clumps, p to the power k minus 1, 2 times p to the power k minus 1, 3 times p to the power k minus 1, and then p times p to the power k minus 1, which is nothing but p to the power k. Now this rather complicated looking permutation has two important properties. The first of which is this: the pth power of sigma is the identity. This is easy to see. Why? You see, because we have constructed sigma in such a way that the first cycle in sigma uses only the first elements of all the clumps. The second one uses the second elements of all the clumps, and so on. So sigma is a product of disjoint cycles. These cycles are all disjoint. No two cycles have any element in common, and that is why they commute among themselves, which means that the pth power of sigma is actually equal to the pth power of this first cycle times the pth power of the second cycle, and so on up to the pth power of the final cycle, because of this commutation. Otherwise it's not true in general. For example, in a commutative group, it is always the case. We are now not in a commutative group, but at least the cycles commute among themselves, so the powers behave like this. But all these pth powers are equal to identity. Why? Because each cycle is a p cycle. Why is each cycle a p cycle? That's because we are using p clumps, right, in forming each cycle. The elements we are using in forming these cycles are different, but there are p clumps. So that is why each such pth power of the cycle is equal to identity. So that's how we get E. But the second one is a little difficult to understand. Let me first write it down and then we will see what it says and why that is true. Let tau in sp to the power, that means it's the permutation, be such that it fixes any I greater than p to the power k minus 1. Then sigma inverse tau sigma possibly changes only we will write the clumps again, okay, don't worry. Will possibly change only elements of the second clump of the set the author writes, but let's write the second clump. It becomes easier to understand. Second clump, that means what is the meaning of this statement? Tau is a permutation which fixes any I greater than p to the power k minus 1. What it means is that what does every permutation in this group do? It changes the symbols in whatever way it is, I mean whatever way it wants, how the permutation behaves, that's how it changes the symbols, because it's after all a function. What this part says is that in the set of all symbols, tau actually does not change any symbol that exceeds this. That means tau has no effect on that part of the set of symbols. Or, to be more precise, tau does not change any symbol on that part. Whatever tau does, it does in this region. That too, actually tau may not change anything at all. Tau may be identity. But even if it is not identity, its effect, its action is confined in this part only. That's what tau is. Nothing else is known about tau. Then what we are saying is that sigma inverse tau sigma, this conjugate element, possibly changes only elements of the second clump. It does not change elements of any other clump. Why? To see that, we have to briefly again write down the clumps. The second clump we already see here. So let's write the first clump. And then let's write the third clump. And finally, let's also write the final clump. Let us first see. So what we are saying is that this changes only possibly the elements of the second clump. Why does it not change the elements of the first clump? Let us see first that. Let's arbitrarily choose any element of the first clump, say 2. So to see what this element is going to do to 2, that means we are now looking at this. Do not forget that we have already decided, and we are continuing with this convention, that we are going to write functions to the right of arguments. This is not the standard way of applying a function to something. Here our function is this, and this is the argument. Okay. So let us now see. So that means sigma inverse is first going to be applied to 2. So where does 2 lie in sigma? Here. Sigma inverse. So what does sigma do to 2? Sigma changes 2 to the next one. So sigma inverse does the opposite. It takes 2 in the other direction. That means it will map 2 to this element. Where does this element lie in the clumps? In the last clump. And then on this element we have to apply tau next. Does tau have any effect on this element? No, because it lies outside the region of influence of tau. That is why when we apply tau on this element, it does not change, it stays as it is. And then on that, finally when we apply sigma, it gets mapped back to 2, because that's what this cycle does, right? So that's how 2 remains 2 under this permutation. There is nothing special about the element 2. Anything else you choose from the first clump, say p to the power k minus 1. Where does that appear? Here in the last cycle. In which cycle it appears, you can pretty much see, actually has nothing to do with the current situation, but the position of the element in that cycle with respect to the other elements is what matters. On this, if you apply sigma inverse first, it will map the element to p to the power k, on which again, just like that 2 case, tau has no effect, because p to the power k is in fact far from the region of influence of tau. It's in fact the farthest away. So tau of p to the power k, or p to the power k tau, is p to the power k itself. On that, finally when you apply sigma, it gets mapped back to p to the power k minus 1. And that is the case with any other element of the first clump. So that's how this has no effect on the elements of the first clump. The elements of the second clump possibly will get changed under this, so we are not going to say anything about them. But what happens to the elements of the third clump? Let's see. Now we have become a little smarter, so we can speed things up. Where does this lie? 2p to the power k minus 1 plus 1 in sigma. It lies here in the very first cycle as the third element. So on this, when you apply sigma inverse, of course it will get mapped onto this p to the power k minus 1 plus 1. On this element, does tau have any effect? Is it going to be changed by tau? No. It is greater than p to the power k minus 1. It is just greater than p to the power k minus 1. We have come as close as we can to the region of influence of tau, but we are not entering that region. We are safe. So this also remains unchanged by tau, and when on that you apply sigma, it gets mapped back to this. Yes, and that is the case with, in fact, any other element from the third clump, because all of them are going to be third elements of the cycles. Apply sigma inverse on that, it gets shifted to the left on any such element in the second positions of the cycle. Tau has no effect. So the element ultimately is going to go back to the original thing. So that's how the third clump also remains unchanged by tau. And you can see that this is going to be the case when you go further and further away on that side, that is with the other clumps, with elements of the other clumps. In fact, this is the most dangerous situation as far as something that may be changed by tau is concerned. But this is the closest we can come. So that's why, yes, sigma inverse tau sigma actually possibly changes only the elements of the second clump. Now let us see the next one. The author doesn't say anything about the by next one, I mean we have minus 2 here and 2 here. The author just simply tells us the general statement, but let's see one more so that it becomes clear. This element possibly changes the elements of the third clump only, and the third clump of course is this. Why not the second clump? Why not the first clump? Let's see what happens to the elements of the second clump. The second clump we have here. So, oh, I have lost sigma, no? A part of sigma. Let me just write it here. So let's pick this one. On this, we are now going to apply not sigma inverse tau sigma, but rather this. Okay. So where do we find this in the among the cycles in sigma? Is it going to? Oh, it's here. Okay. It's appearing here. So when we apply sigma inverse, it first gets changed to 2, and then on that 2 we are again going to apply another sigma inverse. So that comes here, and on this again, just like before, tau has no effect, so it stays the same under tau, and then we are going to apply sigma square to it. So sigma square, first one sigma maps it to 2, and then another sigma maps it back to the original element. So like that you can see the other cases also, and you will see that in this case possibly only the third clump elements are going to be changed by this, and in general this is going to happen. In general, possibly changes only elements of the j plus 1th clump, which of course is going to look like this. How do mathematicians come up with these things? I also wonder. It takes time. All right. So much for properties of this sigma. Okay. So now we are next going to consider a subset of our group. This subset. In other words, in A we are considering precisely those tau that we were considering there. Okay. Note that tau is a permutation which does not change anything, any symbol above this number. Note that the identity permutation belongs to A. Why? Because identity actually does not change anything at all. So in particular, it also won't change this type of i's. That means it belongs to A. That makes a non-empty subset of this group. Also, A is clearly closed under the product in our original group. That is, if you take two such permutations, tau 1 and tau 2, none of them changes such an I, then their product also will not change I. In other words, A is a non-empty subset of sp to the power k that is closed under the binary operation. Hence, A is a subgroup of s p to the power k. And in fact, you can see that the permutations in A actually have their effects only on this set, the set of the first p to the power k minus 1 positive integers, which is why this subgroup A in fact is just like another permutation group, namely sp to the power k minus 1. In fact, A is isomorphic to this. You remember when we said that these are the only restrictions on tau. Tau can do whatever it wants in this region. Tau can do whatever it wants in this region, and precisely that type of permutations make this group. So that is why A is isomorphic to this. If you want to really go through the details, you need to make these ideas rigorous. But this part I am not going to discuss. Okay, it's extremely easy. You convince yourself that this is the case. So now we have come to the next lower symmetric group of this form. So here we can apply our induction hypothesis by the induction hypothesis. A has a subgroup P1 of order, namely the order that should be for the P Sylow subgroup here in this group, or here same thing, that is p to the power n of k minus 1. Okay. Now we should consider this. T, which is P1 times sigma inverse P1 sigma times sigma to the power minus 2 P1 sigma square, like that. The final factor is this. So you do understand that here we are considering a factor of not permutations but groups, subgroups. The first one is P1, and this one, do you remember that this is the conjugate of a subgroup by some group element, which in one previous exercise we proved that this is also a group. Similarly, this is also a group, and not just that, these groups, all of them have the same number of elements. That also we proved in that previous exercise. In general, this need not be finite for this to happen, but in our case it's finite. So they have the same number of elements. And in fact, let us write like this: P2 up to P, where Pi is this, or if you want a simpler definition of these Pi's, then it's just this. For I varying from 1 to P minus 1. Okay, now you recall what we did just now with all those sigmas and everything. You take an arbitrary element of P, okay, say tau, of P1, because P1 is after all a subgroup of A. This tau is in A, and in A what are the types of elements that you have? Namely those tau which do not change any I that exceeds P to the power k minus 1, and for that type of tau we left behind an entire story, right? That sigma inverse tau sigma behaves in this way. It changes only the elements in the second clump. Similarly, okay, so I was getting ahead of myself. So for this tau, there is one element here, right? Sigma inverse tau sigma. In fact, what I am trying to say here is that an arbitrary element of this is going to look like this for some tau. Now, if you take any other tau from P1, say tau prime in P1, tau prime by the definition of A, because P1 is a subgroup of A, is going to have its effects only on elements or only on symbols that are less than or equal to P to the power k minus 1. That is, the effect of tau prime is confined within the first clump, but the effect of sigma inverse tau sigma is confined within the second clump. Similarly, the effect of any other element from this subgroup is confined in the third clump. So that is why these permutations have their own regions of influence in the set of all symbols, and that is why they commute. Because if you express tau prime as a product of disjoint cycles, in that product representation only these symbols are going to appear. However, if you express this as a product of disjoint cycles, it will have one such decomposition. Only the elements of the second clump are going to appear in those cycles. That is why these permutations also commute. And this is the case with all the elements taken from all the subgroups that you see here. That is why the author writes what is the exact language that he uses. He says elements in the distinct PIs influence non-overlapping sets of integers. Sets of integers. So they commute. And we know that when they commute, the groups commute. That is, P1 times this is this times P1, so that their product is a subgroup itself. Similarly, this is a subgroup and the elements of this product commute with the elements of that next subgroup, because they also influence non-overlapping sets of integers. So this times this is equal to this times this product. So the product of the first tree is also a subgroup, and like that continuing, we get the fact that T itself is a subgroup. Hence, T is a subgroup. Note one more thing, that although P1 is a subgroup of A, but the moment we have formed the conjugate by sigma, we are no longer necessarily inside A. That's because sigma is not in P1. Sigma is not in A. Sigma actually does not keep those i's fixed which are greater than p to the power k minus 1. Sigma, if you go back to the definition of sigma, it changes everything. All symbols it changes. Okay, so T is a subgroup of, in general, S p to the power k. But also due to this non-overlapping nature, any two such distinct PIs intersect in a trivial manner. Hence, the order of T is, by an extension of the formula for the order of the product of two subgroups, order of hk divided by order of h intersection k, because the intersections are all trivial, so it is the product of the orders of all these subgroups. However, just now we have said that because these are conjugates of one another, all of them have the order of P1. So an order of P1 is what? This. How many of them are there? P. So this is the order of T. But this is not what we want. This is not the P-Sylow subgroup that we are seeking of Sp to the power k. Something else is. To get to that, we have to take the product of P and something else. The proof is fairly complicated, I must admit. So the thing we have to now consider is this. P, which is the product of the cyclic subgroup generated by our original sigma and T. Is it a subgroup? First of all, we have to see that. Now let's go back to what T is. T is this. Na? Originally T is this. We are again writing everything because we are now going to see something carefully. What happens when we form the conjugate of T itself by sigma? Obviously, that is, it can be written like this. That is, each one gets replaced by its conjugate by sigma. So in place of P1 now you have this, in place of this you have the next one, I mean it becomes the next one. That's because the intermediate terms, there are some cancellations there. Sigma and sigma inverse together, sigma to the power minus 2 together will give you this sigma inverse here. Similarly, if you write another one, sigma square times the next sigma to the power minus 3, is it going to be minus 3? Let me write that and see. I need to myself be really clear. This one becomes this, so that this one and this one gives me what? Maybe I am getting something a little wrong. Or maybe I am unnecessarily making it more complicated than it needs to be. Yeah, why go back to the original form when we have a better notation? We had this, right? P. And we just need to use this definition of the PIs, right? With that, if we form this conjugate, we will realize that actually, you see, when you form the conjugate of this product, that is actually nothing but the conjugates of all the elements. Yeah, now it will come. In this fashion, it's easier to understand. this becomes, the suffix increases by 1. P2, P3, like that. Eventually we reach PP, which comes from the previous one. But what about this one? Let's see what this one is actually. Originally it was this. Right? So together, if you take all the sigmas together, you are going to get what? Sigma to the power minus p, p1, sigma to the power p, and this is where that fact that sigma to the power p is e is going to be used. So we have p1. However, we already know that these things commute among themselves, so we can bring things back in the original order. So we get t, and from this entire thing we are going to get what? T sigma is equal to sigma t. What it means is that sigma commutes with all the elements of T. That's what it means. Is that what it means? Sigma commutes with all the elements of T. No. What am I saying? That's not what it means. It means that this right coset of T is equal to the left coset of T by sigma. Hence, you are going to get this. Exactly how this one follows from this one, I'm not going to elaborate on that. Okay, you figure it out yourself. The fact is that we get this. So, because of this commutativity, P is a subgroup of Sp to the power k. Now the next thing we have to see is this. Sigma is not in T. Why? Suppose sigma is in T, then sigma is going to be of this form, belonging to Pi. Okay. Now, for any I greater than p to the power k minus 1, what will happen if you apply that I to sigma? If you apply sigma to that I, you have this, right? But because all these sigmas commute among themselves, and the thing is that these other sigmas, sigma 2, sigma 3 up to sigma p, they do not have any effect on this I. Okay, so that is why this is equal to I sigma 1. I think I messed up again. What can I do? It's a long video. This is wrong. So for any I in this part, in this part, that is in the first clump, this is where the other sigmas other than sigma 1, they do not have any effect. How am I able to write suddenly only this? That's because you can change the orders of these things, right? They commute among themselves. So if you bring sigma 2 in the front, then I sigma 2 is I. So like that sigma 2 vanishes, and like that everything else vanishes. Only sigma 1 remains. Okay. But this is a problem. This is a problem because sigma 1 fixes everything greater than p to the power k minus 1. That's because sigma 1 has its effect only in this region. However, sigma changes everything. Sigma does not fix any element. So that is why this is a contradiction. Hence, our supposition is wrong. That is, sigma cannot be in T. In other words, sigma is not in T. But that in turn implies that the cyclic subgroup generated by sigma and T intersect trivially. Which is why it's not just that this P is a subgroup of Sp to the power k, but we are now able to calculate its order like this. Also, that means besides it being a subgroup, we also have this. The order of this cyclic subgroup times the order of T. Now because sigma has itself order P, so this is P, and you remember the order of T, it was P to the power P times n of k minus 1, and that is P to the power n of k minus 1, that is P times this plus 1. And if you go back to the formula for nk, what is this? This is 1 plus P, like that it goes up to P to the power 1 less than what you have here, k minus 1 plus 1. This plus 1 is in the exponent, okay. So finally you have this. Which again by that previous lemma is this. So now we are finally done. P is our subgroup, P Sylow subgroup that we were seeking, and the proof is over. There is a numerical illustration of this proof which we will discuss in the next group theory video. Okay, so I'm going to end this long video here. I feel like I have messed up in some places in this proof. So if you find any inconsistency, please ask in the comment section below. So that's just it for tonight. And tomorrow we have our usual analysis update. So see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.